Hi, and welcome back. So let's do another one of these final review problems. The distance from the Sun to the Earth is 1.496 times 10 to the 8 kilometers. How many positive crests are there in the path of a photon traveling from the Sun to the Earth with a frequency, of 4.17 or 4.74 times 10 to the 14 cycles per second? Okay, so probably the very first thing to do if you see this on a final exam is to not get too incredibly worried about it, because this really is not that difficult of a problem, or it might seem kind of difficult, but if the most important thing to not do the most important thing to stay away from doing if you see this on a final exam is to get really distressed about it. So that's the very first thing to not do, is to maybe take a deep breath if you see something like this. The next thing is, okay, so what are they asking for? We have a distance. It's the distance from the Sun to the Earth, 1.496 times 10 to the 8th kilometers. And we're given a frequency. And then in that frequency, we're supposed to figure out how many positive crests are there in a wavelength. And if you remember, what does a wave look like? If we have, let's just call this our photon, and our photon is moving in some type of wave, goes up like that and comes down like that. And this distance from here, I guess this zero crossing point to this zero crossing point, this is one cycle. Okay, so this is one cycle of our wave, and you can imagine if we kept on drawing, I'll just change colors for this, but if we kept on drawing cycles of the wave, we would just keep repeating cycles again and again. I'll just keep changing colors. There we go. So if we kept on drawing cycles of this wave, we would just, we would keep on going up the cycle and then come back down the cycle and then up and down. And each of these different colors, so this blue section is one cycle, this yellow is another, this orange is another cycle. And so now, where does wavelength fit in to this diagram? Well, the wavelength is pretty much the distance encompassed in one cycle, right? So this distance right here is going to be our wavelength. So now, we didn't necessarily explicitly get wavelength, but we got frequency. And if we know frequency, we can definitely get wavelength out of this information. And before we do that, maybe I'll just do one more aside and just, imagine, this won't be drawn to scale, but imagine that we have, let's say, I'll draw it nice and orange. So imagine we have the Sun. So this is the Sun up here. There we go. So there, that's the Sun. And then Earth is going to be all the way over here. So this is Earth. And now we've got our photon that's traveling. We know its frequency, the photon that's traveling from the Sun to the Earth. And if we were just going to draw the path of the photon, it would look something like this, right? We would have our wave across the distance from the Sun to the Earth until it eventually got to the Earth. And we know this distance, right? We know that the distance, so I'll label this, that this distance, d, is going to be equal to this, right? It's 1.496 times 10 to the 8th kilometers. So 1.496 times 10 to the 8th kilometers. And we also know, and hopefully I've shown you down here, that when we have a wavelength, pretty much per every 1 unit of wavelength, so we could figure out, actually, you know what, that might be a good thing to do. Actually, you know what, yeah, I'll do this right now. What is what would be the wavelength of our photon with this frequency? And remember, what is frequency denoted as? Frequency is denoted as, sorry, I keep on drawing lambda. Frequency is denoted as nu, right? And if you remember the corny chemistry joke, what's nu? Nu is c over lambda. So anyway, so we can, and what's c in this equation? C is just the speed of light. It's 3.00 times 10 to the 8th meters per second. So hopefully you can see that based on us knowing what nu is, based on us knowing the frequency, we can figure out what the wavelength is. So what would the wavelength, if we wanted to just figure out our wavelength lambda, what would lambda be? Well, lambda would just be c divided by, draw a better nu, c divided by nu, right? That's what lambda would be. So let's actually set that up. So we can say that what we're looking for, our wavelength, so what our wavelength is, and this is our wavelength down here, is going to be equal to 3.00 times 10 to the 8th divided by 4.74 times 10 to the 14th. Okay, and let's actually, I'm just going to work out the exponents on the side here. So we can say that this is going to be equal to the same thing as 3.00 divided by 4.74. And then if we bring, if instead of dividing by 10 to the 14th, we multiply by this term, it's just going to become, we're going to multiply by 10 to the minus 14th, right? So we just multiply times 10 to the 8th times 10 to the minus 14. And what do we do if we're going to multiply by 10 to the minus 14? Or what are we going to do with this expression? Well, we can just add these two exponents together, right? So we could actually combine this whole thing to be, what is 8 minus 14? Well, that's going to be, what is that? That's going to be minus 6, right? Minus 6, or 10 raised to the minus 6 power. So now I think we're ready to go and get out the calculator. There's my calculator. Okay, so we've got 3 divided by 4.74. And we get 6.329. So 6.329 times 10 to the minus 6. So this is equal to 6 point, or else, actually no, it's not. It's equal to 0.6329 times 10 to the minus 6, sorry. 0.6329. And actually we only have 3 significant figures, so it's 0.633 times 10 to the minus 6th. And what if we wanted to, and this is something that we can do, and it might make sense to do because we're talking about the wavelength, and it looks like we've got a wavelength that might make a lot of sense to represent in nanometers, which is, nanometers is something, would be this time something times 10 to the minus 9th power. So if we wanted to have this, instead of being minus 6, we wanted to have a minus 9 here, what would we do? We would just move this decimal place over 1, 2, 3 positions, right? So if we said we had 633 times 10 to the minus 9 meters, that would be the same thing. This unit is meters too. So and then if we wanted to do that, we have 633 times 10 to the minus 9 meters. We can even write that as 633 nanometers. So this is going to be our wavelength. This is going to be our wavelength for the wave of our photon, our wavelength of light. So now we figured out what our wavelength is, and now we have to figure out how many positive crests are there in each wavelength. And you can hopefully see from this diagram, each wavelength, and hopefully you can see that each of these, so right here, this is another wavelength. This is another wavelength. This one in orange right here, this is another wavelength. And each one of these has got one positive crest. So we have got one positive crest for every single wavelength, for every single wavelength that we have in between this distance traveling from the sun to the Earth. For every wavelength that we have all the way through this entire distance, we are going to have one positive crest every time we complete one of these cycles going through this waveform. So now, how would we figure out how many there are total? Well, we would just figure out. We would divide this number. We would want to figure out how many of these wavelengths, how many of these. Let me go down here, and maybe I'll just write this again up here. How many of these wavelengths of 633 nanometers fit into this distance of 1.496 times 10 to the 8th kilometers? How many of these wavelength distances fit into this overall distance from the sun to the Earth? So in order to do that, let's just set up our conversion factor. And again, I'm just going to say that our wavelength, so I'll just write this over here, that our wavelength is equal to 633 nanometers. And so now, what can we do? We can say that, so let's start out with our distance here. We have 1.496 times 10 to the 8th kilometers. And we want to convert that pretty much into wavelengths, right? We want to figure out how many wavelengths this is. So let's first off start out by we're going to convert kilometers into meters. So we have 1 kilometer is equal to 1,000 meters. And then let's take meters and convert into nanometers. So we can say that 1 meter is going to be the same thing as 10 to the 9th nanometers. So now we've got nanometers. And that's the same thing that our wavelength is measured in, right? We've got our wavelength is 633 nanometers. So now we can say for every single so now we can say if we want nanometers to cancel with nanometers, we can put in 633 nanometers is going to be equal to, and actually, you know what? Sorry, I'm just going to erase this so I've got a little bit more space. So 633 nanometers is going to be equal to one cycle of this wave. So one cycle going up and then coming back down and coming back to our zero crossing point. So one cycle is going to have a length of 633 nanometers. And then the last thing that we could do, and this kind of, I guess, rounds it off a little bit, but we could just finally say that for every one cycle, we also have one positive crest. And that's pretty much it. We've figured out, we've just, essentially what we've done is we've divided this distance that we have, this 1.496 times 10 to the 8th kilometers, this distance between the sun and the Earth, by this distance which encompasses one cycle of this wave. So hopefully you're following this okay. And then we've also been able to say that for every one cycle we complete, there's going to be one positive crest inside that one cycle. So now we're pretty much done. We're ready to just throw all of this into the calculator. So now let me get out my calculator. And one thing I am going to do again is just remember I'm going to put on all of my scientific notation at the end of this. So we could say that, at the end I'm going to have 10 to the 8th times 10 to the 3rd times 10 to the 9th. So what's 8 plus 3 8 plus 3 is 11, plus 9 would be times 10 to the 20. So we are going to say that whatever answer we get out of the calculator is going to be times 10 raised to the 20th. So let's just go ahead and get out the calculator. So we have 1.496. And then the only other thing we have to do is divide that by 633. So divide by 633. And we get out 0.00236. So 0.00236. So I'll write that down. 0.00236 times 10 to the 20th. And now what's the last thing that we could do? Well, we could move this decimal place over a few places, right? And we could move it over 1, 2, 3 places, which give us, so we could say our final answer, if we move this decimal place over 1, 2, 3 places, we would say that this is equal to 2.36 times 10 raised to the 17th power positive crests in our waveform. And this would be our final answer. So anyway, hopefully I've hopefully shown you that if you get a question like this, and this is, it's really, hopefully I've shown you that this question isn't really so terrible should you see it on a final exam. It's not that terrible. It might be, a little bit intimidating when you just get this block of text like this and you think, oh, I've got to compute this, enormous number, and I'm given this enormous number, the distance between the sun and the earth. I've shown you that it's not too terrible to come up with an answer to a question like this. And we've got 2.36 times 10 to the 17th positive crests in our waveform. So anyway, thanks so much for watching, and I guess I'll see you in a future video. Thanks for watching.